together till February, and then exam, and then bye-bye. We'll be friends as before. Class of Power Electronics will be held by me and me only. No teaching assistants, no assistants or everybody else. My name is Franco Maddalino, Franco Maddaleno in Italian. And you will find me at my standard email address, that is franco.maddalino@molito.it. I read it every day, obviously. Or you can reach me by phone. My phone number is 4042. If you want to have some extra explanation, you want to see me in the office, my policy is open office. That means you can drop at any time, but be sure that I am there and I have time. So before coming to my office to ask for explanations or so, give me a call to this number or an email. I tell you when you can come. There will be another opportunity for questions, asking questions besides in class, obviously. It will be explained in a few moments. Okay? That's good. Class is Power Electronics. We will use basically 2 or 3 study supports, books or so. The first study help you can have are your notes. You have to take notes. Because when you write a note, the very fact of writing down a note has the property to fix it better in your mind, in your brain, just better than just listening to what I say. Reason is that when you write a note, you cannot write each single word I say. You have to synthesize it. You have to understand what I am telling you and write it down. And so it helps you to remember. It's a quite effective way. Then you will have 2 possible sets of notes. One is a PDF file, is online, is already online. There is also an errata for it. It's called Power Electronics, what a fantasy. And you find it on the website. Those are the notes of a student a few years ago. He wrote those in LaTeX and compiled and made all the drawings. A very good job. Those are notes. Real-time notes, or almost real-time notes. That means some expressions are not very high level, high standard English level, or a few equations are wrong. There is an errata on the website with a list of errors. I know about it. If you are interested to go on, improve this stuff, that means fixing the errors, improving some sections. I have to add some sections that are not over here. Let me know, and you can work together. It will be very well paid. Let's say I can buy you a coffee or so. So if you want to work on this is in English. This is available on the website. If you are Italian-speaking people and you prefer to read, to study in Italian, there are those notes. Title went away, well off. It's called Alimentatore Commutazione. You find it at Politeco Copy Center, that is in Corso Einaudi, I don't know what number. You have to look for the second volume, part A and part B. There is a first volume that we don't use. It was used when the class was 12 credits, 12 units long. We will use only the second part, the second volume, part A and part B, are about 600 pages. We won't go through all these 600 pages because the class is short, but you have here a good amount of what we will do. Those are Italian, are mainly handwritten with a very good handwriting, not like my handwriting that you will see on, you already saw there on the blackboard. Both contain exactly the same subject, though both are taken from my lecture, so I will more or less go on with the same sequence of the subject, with the same notation, with the same method also. I do repeat, if you are interested to work on these notes, LaTeX notes, we can give you the original files, and we have to fix errors, we have to improve sections, and so on. There are many power electronics textbooks out there. A couple of them are indicated on the class web page. One is Maximovi Ericsson, Fundamentals of Power Electronics. It's a book that is so thick, probably 1,000 pages or so. It's quite theoretical. It's a very good book, quite theoretical, and oh, this is the last one. You know the story. It's very theoretical, but very in-depth. It's a good book. I will stay a little bit more on the practical side. I mean, I teach you some theory and how to design circuits. This is a design class, not a theoretical class. The other one is Kasakian, Schlechter, Gies. I don't remember the title. It's something Power Electronics, Principles of Power Electronics. This, I think, is not in print anymore, but you find it in the library if you are interested to see what else is going on power electronics, what's going on in power electronics. These notes are more than enough for the class. I mean, if you study on the notes, it's okay. You don't need anything extra. Okay? So far, so good. Classes. Schedules. We have 2 lectures per week. It is on Tuesday. Now, 8:30. That is a very bad time because I am still sleeping. I seem to be awoke and talking, but I just painted my open eyes on my glasses this morning and I am going with my autopilot. Tuesday, 8:30, 3 hours, ouch. And Friday at 10. Okay, I have to put a reminder because I'm used to 10:30, so if I am late on Friday, it's just because I'm absent-minded. I forgot it was 10. We try to come at 10, yes, I usually do. At 10 for 1 hour and a half, that is better. And then we have lab on Tuesday, that will be same day as today, at 4 p.m. It's a very late time because it lasts till 7 p.m. Now, good news. Lab is not mandatory. You don't have to come to the lab. If you are interested, you want to come to the lab, you are very welcome, but it's not required. There is only one subject that I will teach in the lab because it will be obvious from what you see on the scope, but I will repeat it in class, so it's not a big deal. Lab can be helpful to have some experience hands-on. Lab can be helpful to fix these concepts, the power electronics concept, what I tell you in your mind, but it's not required, it's not mandatory, it's not giving you more a higher grade, more points for the final grade or so. There is another problem. This is just a bureaucratic problem you don't have to be involved with, but we will have only 1 or maximum 2 official labs. That means I will write it down on my logbook, etc. The other Tuesdays will be absolutely free. I mean, I tell you, this afternoon, not this one, Tuesday afternoon, I will be in the lab. Lab is lab 17. LED 7, not 20, LED 7. I will be there, sorry, 8. I told you I was still sleeping. I will be in lab 8 at 4 p.m. If you are interested and you pass by, come to say hello. If you want to make some experiments with the power electronic circuit, you are very welcome. And I will be in this laboratory available for questions. So the official lab will be probably only next week, next Tuesday. There will be official, etc. And everything else is up to you. If you are interested, pass by, come by, drop by, and we will have some fun. If you have questions, you can come. It's a very good time to ask the questions. Okay? This is just for a bureaucratic rule that came out for the Polytechnic a few years ago, so it forced me to do something like that. Lectures will be taped, and I put this lecture online. Probably you will have them by the next, before the next lecture. Not so sure, because I have to compress work on the file, and then I have to upload it, and then the Servizio Audiovisivo, whatever it is, the name of this service, has to move to the right website. It takes a few time, some time, but not too bad. What else? Exam, maybe? Are you interested in exam? Exam is written and oral, both of them, both in English. Written exam has a first part, half an hour, with 5 or 6 theory questions. No derivation, no mathematical derivation, just maximum I will ask you for a description of mathematical stuff, but not deriving equation or so. Or basic concepts, I will ask you for basic concepts that you should know by heart, just telling me, oh, it's like this, blah, blah, blah. And then, after these 30 minutes closed books, I will give you a design project, a design problem, and I'll give you 2 hours to design circuit I give you. It will be open book. You can use everything you want, notes, your notes, examples, whatever you want is fine, except your classmates.
Computer?
Pardon me?
Laptop?
No, not laptop, because laptop have a Wi-Fi connection or calculator is more than enough. If you forget your calculator at home, no big deal, you can do your math in your mind.
Mobile phone?
Pardon me?
Mobile phone?
No. Everything that has radio frequency is not okay. Oh, by the way, a mobile phone is not a calculator. A calculator is a calculator, a mobile phone is a mobile phone. So, written exam. 30 minutes closed book, 5 or 6 theory questions. 2 hours open books, open notes, open whatever you want, except classmates and telecommunication systems, including smoke signals. Smoke signals are not allowed because it's forbidden to smoke in university. After this, a few days after, you will have your oral exam. Oral exam is about 40 minutes or so. My office, we will discuss what you did during your exam. I will ask you some, let's say, more theoretical questions, because you already proved me that you are able to make calculations. So we will just go through details or basic ideas of power electronics. Good news is that the pass ratio of this class is very high. Last year I had about 40 students or so, and there are only 3 of them that still have to pass their exam. Usually, people pass this exam the very first time they come, for a set of reasons. One is that you have enough experience on how to study for university exams, so you know how to study. You are not a freshman or a sophomore that you didn't understand yet how the university works. You are interested, at least I hope, you are interested in this subject, because this is not a mandatory class, this is an elective class. You have chosen to come over here, so in some way you are interested, no? Were you forced to come over here? No?
No.
Did the doctor go to the power electronic class if you want to get better in your life? The pass ratio is very high, something like 90-something%. If you work very hard, but you have really to work hard, you can fail the exam. It means you have to come to make absolutely nothing during the written exam. You have to install my mom. That means not knowing the Ohm's law, etc. This case I say, oh well, probably it's better if you come back next time. But it's very, very rare. In some cases it happens that people come just to see what the exam looks like without having opened any book. I mean, no idea what power electronics is. In this case, I say, okay, come next time, or just cancel this class from your piano di studio, whatever you have now. Load, what is the name? Carico didattico. Teaching load. Okay? In general, almost all of you passed the exam in February, a few in June. In September, I had 3 students. And there still are 3 more that have still to pass the exam from last year. Okay, so far so good. If I forget something, please don't hesitate, don't be shy, don't hesitate to stop me, raise your hand. and ask questions. I don't bite the students usually. OEM, schedule, exam, books, what else? This class will be, as I told you, as you already noticed, maybe in English. Everything will be in English, including the emails you mail me, including the exam. The oral exam will be in English. Many of you know English quite better than me, quite good, better than me. Few of them, and few of you are not probably used to, and best way, as far as I know, to learn a foreign language is to think in that language. You cannot think in Italian and translate word by word. It does not work. It does not work because I don't understand. It does not work because it takes too much time. It does not work because the phrase that comes out will be meaningless. Anyway, try to think in English. If you study in English, you can imagine in your mind how the exam could be, describing how a converter is, how it works, the basic equation, the basic method, etc. One reason for having this lecture videotaped is that you can listen to what I told you. You can remember, maybe learn some new words or so. Oh, remember that power electronics is not important. This class is basically useless, unless you go to work in power electronics field. If you don't work in power electronics field, it's absolutely useless. If you go in power electronics field, this class could be useful. Actually, it's very useful. But what is for sure, guaranteed, always useful is English. Even if you go to design microchips, if you go to design satellite, if you go to organize the buses and trams in Torino, whatever it is, English is far more important than anything else. It's far more important to know English than to know power electronics. It's far more important to be able to tell a joke in English than to know the Ohm's law. It's not a joke. When you will go to job interview, that means you graduate, you go out there looking for a job. Your job interview will have these first three questions. First question will be, how many languages do you speak? Besides Italian and English, because Italian and English is a given. Everybody knows it. Do you speak any other language? Second question will be, are you available to travel or to relocate, even worse? And the third question says, what did you study? Psychology, oh, okay, fine, come. Do you have some common sense? Come. But being able to communicate efficiently in English, that means teamwork in English, being able to travel or relocate. Travel does not mean I know how to catch a plane and to fly somewhere else. It means I know a different culture, I know how to be productive in a different culture, in a different country or so. And then if you know something about electronics, it would help. But I do repeat, English is very important. It's fundamental. No English, no job. Period. Well, no technical job. If you take any non-technical job, probably you can go without English, but it's not so common for you. Okay? If you go to London and you don't speak a very good English, they look at you with a very strange expression, and sometimes they don't understand you. If you go to everywhere else in the world where English is spoken as first or second language, they don't care too much. If you go to the United States, over there are thousands of different accents and idiolects, and they even understand me. So they don't care too much. As long as you can communicate, it's fine with them. So don't be shy. If you have a question, raise your hand and ask questions. I don't bite you. In some very rare cases, I will emphasize some pronunciation because there are words that, especially for Italian students, are not difficult but just said in a wrong way. For example, component. Everybody tells me component. No, it's not component, it's component. It's not my fault, sorry. Or if you look for an MOS transistor has a drain, has a gate, and has a Source, not source. I know that everybody says source, but it's not right. Source. Or the unit for energy. What is the unit of energy in SI? Joule. Joule, not joule. Joule. If you want to be very precise, it could be Joule, because the father of Preston Joule was from Belgium, a French part of Belgium. He was a beer maker. And he moved to England because the beer market was better in England than in Belgium. And Joule was not, Preston Joule was born in England, and it was Joule. Okay? In some cases I will emphasize some pronunciation that is not usually said right from by the Italian student. What else? Who among you got his or her degree from this Polytechnic? From the 1, 2, 3, about and half. Who among you had already my previous class of Circuiti Elettronici? Those are crazy people, because you know me. What are you doing here? Stay away. And who among you does not speak Italian? 1, 2, 3. What is your mother tongue?
French.
Alors, malheureusement, je ne peux pas faire cette heure en français, parce que tous les autres ne comprennent pas, et aussi parce que mon français est un peu rouillé. I used to teach in French many years ago, when my beard was black. I was working in Switzerland, the French part of Switzerland, in Lausanne, for the Polytechnique de Lausanne, but sometimes it was practice French. Anyway. Anything else that usually professors tell you at the beginning of a class? No? Did I forget something about the practical aspects? No? Okay. So, let's start. Power electronics. What's power electronics in general? Well, it's electronics dealing with power. Is there a given power level above which you have power electronics, below that level you have, let's say, signal electronic? Is there a boundary that divides power from signal? No. You have power electronics every time you are worried, you are concerned about efficiency. If you start to say, okay, let's check the efficiency of this circuit, that is power electronics. It has not a very definite level of power. It's not above 1 watt is power, below 1 watt is signal. There are circuits that work with very small power levels, like the circuit in your cell phone, that are power electronics. When you are worried about, you want to improve the efficiency of your system, you are in power electronics domain. And power electronics is basically subject that deals with converting energy, electrical energy. Not mechanical to electrical, chemical to electrical, electrical to something else, to light, etc. It's just electrical to electrical conversion. And we can have three or four different kinds of conversion. For example, we can have a source of electricity that is DC, battery, for example, or something like this, and we want to convert it into a DC to DC conversion. That is one possible conversion that we are interested in power electronics. Or you can have DC to AC. Or you can have, and now you can guess easily what is going on in the last two lines,
AC/DC.
AC to DC, and
AC/DC.
AC to AC. Okay, those are the basic main conversion you can have in power electronics. If you take any, not any, most of the power electronics textbooks that are out there, they deal with all four of these conversions, because all those are power electronics. What we will do in this class is not going through all these different configurations, but we will stay on the DC to DC and a little bit on AC to DC. When I started this class many years ago, I had to choose between having a wide scope class, that means going through all the subjects, all the aspects of power electronics, without going in depth, without analyzing very well, or limiting my scope to just 1.5 fields or subfields, but going into the details, going into the design detail. And I picked this solution. We will go only from DC to DC and a little bit AC to DC, but we will go in very details for these two fields. Very details up down to the level of designing a circuit that works. This DC to DC conversion, this DC to DC circuit is called not usually converter, big fantasy. DC to AC is called inverter. You will have the analysis, the study of the DC to AC that is very important. It's not important, this is very important. In the next semester class with Professor Musolino, what's the name of his class?
Advanced
Electronics, or whatever it is. That will be mainly DC to AC, or bidirectional DC. AC to DC is called the rectifiers circuit. We will see a little bit of these rectifier circuits. AC to AC is possible. Direct AC to AC conversion. It's possible, it's not used anymore quite often, what's called cycloconverters. Or matrix converters. Nowadays are not used so much, because if you have to make a conversion AC to AC, it's more convenient, it's, let's say, easier, even it's also better performances, lower price, etc., to have an AC to DC rectification. So you take your original AC, you transform it to a DC, and then DC to AC. It's in a useless work, because you convert AC to DC and then DC to AC. But it gives you better performances and prices than direct AC to AC. So this is cycloconverters are not used anymore. There are AC to AC converters, but usually are made by a rectifier plus an inverter together, back to back. We will stay on these two fields, in these two parts. The reason is that I am an electronic engineer. I work with electronic circuits, and all electronic circuits require a DC supply. If you drive a motor, an electric motor, you need an AC, obviously. But I am not a motor driver. I am a power supplier for electronics. And in electronics, you have mainly DC to DC conversion problems and AC to DC, because the mains in our houses is AC. You have to convert it to DC, and then you can use this DC to supply your power, your PC, your laptop, your whatever you want. Okay? So the reason is we will stay over here and over here. The power level that you can have in these cases can go from very small, tiny fraction of watt up to megawatts. It's still power electronics. For example, if you have a MEMS motor integrated in a piece of silicon, the power is milliwatts. But you have to generate the controller signals, and so you will have a very small power electronic, but it's still power electronic. Or you can have a conversion, especially DC to AC or AC to DC, in the order of megawatts. Well, we want to go to so wide range or so wide dynamic of power. I will stay in power domain, let's say from 1 watt to 1 kilowatt, where I am working with some ease. But remember, these power converters are very flexible. You can go from very fractional watt to megawatts. One time I was talking to a guy, and we were talking about a very basic converter, a good converter that you will see in a short time. And I was not catching exactly what was his problem. He was telling me about this converter with strange behavior, and I was not getting exactly what he was telling me. So I said, at some point I asked him, what is the power level in the converter? And he answered, oh, it's 5 megawatts. Oh, now I understand why you have these problems. Because for me that circuit was a circuit that was working at 50 watts, 100 watts, 1 kilo, whatever. Anyway, we will stay DC to DC conversion. That will be a big chapter of this class, and some kind of AC to DC conversion. And in any case, we will be worried about efficiency, because efficiency is what distinguishes the power electronics from the non-power electronics. Okay? That's good. Why efficiency is important? And what is efficiency? I should say, to be precise, power efficiency, but efficiency is enough. What is efficiency? Well, efficiency is a ratio, usually is indicated with the letter eta. It's the ratio between the output power of your system divided by the input power. Your circuit does not generate power, converts power. So you need input power, transform it, you change the voltage, you change the current, and you give it to the output, like a transformer. Unfortunately, transformers don't work in DC, so we have to do something more complicated. Efficiency is the ratio of output power divided by the input power. Why is it important? Well, it's important for many reasons. The main reason driving the world is money, cost. If you increase efficiency, usually you decrease cost. But we'll see in a moment why. Okay, I want to say, eta is output power divided by the input power. This number better to be less than 1, otherwise you invented perpetual motion. If it happens that you invented the perpetual motion and you are not sure, come to see me. I double check your calculations. If by any chance you can violate the thermodynamic laws, we can patent it. You don't have to worry about to get your degree anymore. I don't have to worry about teaching this class more times. We can buy one island each on the southern Pacific and spend over there a very good time. But unfortunately, thermodynamics is very hard to cheat with. So this efficiency will be always less than 1, at least in the electric circuit. I have a friend who made measurements on a circuit, and he called me and said, come to see me please, come to my house. Okay, and he came back after the work from the office, and he told me, I was measuring this circuit, etc., and I found something strange, something weird on my efficiency. I said, what was the efficiency of the circuit? He was so shy, he was not able to tell me. He just wrote me down a number. It was 103%. And I told him, okay, let's patent it, or let's find what's wrong with the circuit or the measurements. And quite often, and you will see, measurements in power electronics are not so easy. You can have some strange behavior that can give you an efficiency that is not what you expect, including more than 1. But in this case, quite often many times it's just a measurement problem. Your instruments lie to you. Why efficiency is important? Because, let's say, if I take the difference, P in minus P out, P naught, that means this is my converter, I have an input power over here, I have an output power over here. This difference is positive, because the output power is less than the input power. And what is this difference? The difference is the power that stays inside. Actually, it's not accumulated inside the circuit. It goes out from the circuit in a different form. That would be usually heat. The dissipated power, what is the difference? The input power minus the output power, PV, comes out usually as E. And hot circuits, warm circuits are not so happy. Keep it cool. So, looking for, please.
It's not, this relation is not instantaneous because...
It's not what?
This relation is not instantaneous maybe.
Oh yeah, sure. Good point. This relationship is not instantaneous. It's not P function of t minus the other function of t, because you can have elements storing energy here inside, like a capacitor, and we will see an example of this circuit. So you can have for a given interval of time interval that the output power is larger than the input power, but for a short time. If you take the average, P, average input and average output, you have still this figure. So, why we are worried about efficiency? First reason why we want efficiency, high efficiency is heat dissipation. And heat dissipation has at least two important aspects we have to worry about, we have to take care of. Heat dissipation means high, or could mean high temperature. Let's just say temperature. If you have a circuit working at, let's say, 100 degrees Celsius, and you can have the very same circuit working at 90 degrees Celsius because you cool it down better, just cooling down a circuit and having it running 10 degrees, 12 Celsius degrees cooler, makes your system to live longer. The life of an electronic circuit, the life of an electronic component depends on the temperature heavily. So if you cool it down by 10 to 12 degrees Celsius, what you get is that your life is doubled. Delta T, or let's say about 10 Kelvin, because the difference can also be written in Kelvin, difference is in Kelvin. A delta T of 10 Kelvin means, let's say, negative 10 Kelvin. It does not mean that you are 10 Kelvin below zero. It means that your temperature is 10 Kelvin below. Okay, I am sure that somebody of you will just write down. You work at negative 10 Kelvin, so that's right like this. If you cool down your circuit by 10 to 12 degrees Celsius, your life is multiplied by 2. More or less. This is exponential. Every 10 degrees your life is multiplied by 2. You cool it down by 50 degrees, your life is multiplied by 2 to the 5th. That is 2 to the 5th?
32.
32. And for high efficiency system this is important. So temperature, life, this is one. If you want to dissipate power, you need a heatsink. If heatsink is needed to remove the heat from your circuit. You know how a heatsink works. Did you ever see a heatsink? Yes. It's a piece of usually of aluminum with fins and possibly a fan blowing air through it, or you can have liquid heatsinks that makes a heat pipe with liquid circulating in it and removing heat. Well, if you increase the efficiency, this dissipated power becomes smaller. If your dissipated power becomes smaller, it means that your heatsink can be smaller with the same temperature. That means smaller means less expensive, cheaper, means lighter. Or if you keep the same size for the heatsink, having less dissipated temperature means, the dissipated power means lower temperature, it means a longer life. Dramatically longer life. If your TV set at home fails, you say, okay, it failed. If it's just before a big game, football game or whatever it is, you can say, bad word, it failed, but it's not a big deal. If a component fails inside a satellite, telecommunication satellite, you get troubles. It's not a good thing, because a satellite cannot be fixed usually, not anymore at least, for some time. So there are cases where the reliability, the life, must be long. You cannot fix it, or if it fails, it has very bad effects. For example, let's think to a pacemaker. If your pacemaker fails, well, not a good thing, because your heart will fail with it, and if your heart fails, well, you are not in good shape. So, reliability, life, is important. Or cost. If you need a smaller heatsink, the system will be lighter, will be cheaper, will be easier to sell. And let's just do an example. Let's just make. Let's suppose we need an output power from a power supply. Let's take a PC power supply. Give me an output power that you can have from your power supply into your PC, laptop, desktop.
500 watt. 500 watt.
100.
500. 500.
Ah, 5, okay. Sorry, I'm that. 500 watts. Let's suppose that the efficiency of this stuff is, well, could be the efficiency of a power supply in a desktop.
0.7.
0.8, 0.85, 0.9.
Depends. It depends.
It depends, obviously, but the other magnitude is between 0.8, 0.9 or so. Let's suppose, just to make the calculation easy, let's suppose the efficiency of this is 0.9. It means that the input power is 500 watts divided by 0.9. And 500 divided by 0.9 is 555.6 watts. The very unfortunate guys who took the electronics, to put the electronics class with me, they know that I like to make my math in my mind. Mental math is very important for engineers. Just to have another magnitude. I don't require to have 10 significant figures right, but a good estimate in your mind is very important. Anyway, do we have something like this? It means that dissipated power, the power that you have to remove from your power supply, be dissipated, is equal to P in minus P naught of this O subscript to be read as P sub O. It's very formal, I will never use it. Or you can read it as P out, output power, that's okay. Or you can also say as P naught. Not my fault, sorry, English is like this. Naught is spelled N-A-U-G-H-T. This is 56 watts. How much power you have to remove? It's a lot. Don't care too much about how much is 56 watts. Probably you need a small fan or something like this, but this is not the point now. Let's suppose that, and today I made a mistake, I forgot in my office my hall of chalks. Let's suppose that we are able to increase our efficiency, the new efficiency goes to 0.95. Is it a big deal? No, because from 90 to 95 is just a small change, apparently. But if we go to check, to make the same calculation, what do we get? We get the input power P in in this new case, because we were smart, we were good to improve our efficiency, equals 500 watts divided by 0.95, and this is about 525 watts, the input power. The dissipated power, change, the power that does not come out from the output, and just to make this guy happy, I should say the average power was the guy, just to make you happy, the average power, and thank you, because it was something important that I forgot. The average power that goes into is 525 watts, and the difference between input and output is 25 watts. We had 55 watts, 56 watts to dissipate, now it's 25, 26, something like this. It means that my heatsink can be 1/2 as before. It means that my weight is smaller. It means that my size is smaller. That's important. So you see that even what looks like to be a small change over here gives you a large difference over there, because you have the difference between the input power minus the output power. If you evaluate the sensitivity of this function, it has a large sensitivity. Okay? So first reason why we want high efficiency. Dissipated power. We waste less power. We have a smaller system, a cheaper system, or we have a system that runs cooler, runs at lower temperature, and it has a longer life. Oh, by the way, life is, I gave you this number, but let me write down the exact equation. Life of your system, temperature T equals life at the reference temperature, life of T naught, times two to the power of T minus T naught minus T over, how much did I say, 10 Kelvin, 12 Kelvin, something like this? 10, that's it, 10 Kelvin. Did you ever see an equation like this? Yes, say yes, please. Even if it's a line, say yes. Or diode equation is, but the diode equation has not temperature in it. I'm looking for something that has temperature in an exponential form.
And the capacitor.
Temperature. Chemistry.
Arrhenius law.
Yeah, that's it. Arrhenius law is the activation energy for a failure, depends exponentially on this stuff. It's not nearly 10 Kelvin, it's probably closer to 12 Kelvin or so. And if you have to make an evaluation of the reliability on a system that has to be reliable, don't use this equation. Go to an expert on reliability and ask him or her, please make this evaluation for me. It's a very tough job to evaluate the reliability. Unless you become a reliability expert, ask to an expert to solve the problem. Okay. So first reason why we want a high efficiency is temperature or reliability. Science. Second reason why we want high efficiency. All the power we waste from heat is power that we pay but we don't use. So our electric bill will be higher if our system has a lower reliability, lower efficiency. Is it important? Yeah. Let's say saving 25 watts in your PC, desktop, is it important?
Yes.
Well, 25 watts out of 500 is 5%. You don't see on your electric bill. Yes, but now let's change the scope of this observation. Let's change the point of view. Let's consider the AC adapters. What is an AC adapter?
Power supply.
Power supply that you connect to the mains and you use to supply your laptop, to recharge your batteries, to recharge your cell phone, and so on. Is it important to have a high efficiency in these AC adapters? How many AC adapters exist in Europe?